All right, so now that I talk about the scientific culture of Thai academia and things that I do not totally agree with, right? Longer breakdown than anticipated, as you have guessed. And also there's a key reason why I give you all the Miracle Machine talk, right? Because I love that talk because it kind of touched on things that put Thailand on speed bump in terms of research funding and how misguided research funding is treated in Thailand. Anyway, so let's switch back and now come back to the topic that we need to talk about today, out of order execution. So this is basically the key design in many processors that you see nowadays, except for the GPU. When we learn about the GPU, I'll talk about how it's done. GPU doesn't use out of order execution. It uses a totally different technique to make it fast. But for your CPU, the reason why your CPU is blazing fast partially is because the out of order execution. So to talk about out of order execution and to continue on some of the what are the register aliasing table and all those things, right? We need to first talk about dynamic instruction scheduling, because what we've seen so far, the software would schedule all the instruction through what? So who generate assembly for you? Let me ask you this question. If I write a program, who is responsible for generating assembly? So who is responsible for generating the assembly code for you? Let's say you finished writing a C code or C++ or Java or Python. How does it get converted to assembly? Compiler. Yes, exactly. Right. So you can use the compiler to generate assembly code for you. And the instruction will come into your pipeline in the same order, right? And it execute instruction in order, right? And as we've seen so far, you can actually now schedule an instruction dynamically. Let's say your old instruction is waiting for some data, haven't finished yet. What we can do is to have those future file and everything, then you run basically execute ahead of that code, right? Future instruction, as long as they're not dependent on older instruction that's still being done, you can start right now. So that's the key concept behind out of order execution. But because we now talk about not just how the instruction window is done, right? Now we talk about how do you dispatch? How do you dispatch? Like, let's say I have a bunch of instructions in my instruction windows. Which one can be dispatched? And how do you actually implement this in hardware, right? So the key here is we want to dispatch instruction in order. How? We can move dependent instruction out of the way and issue whatever operation that has all the source ready, right? Again, the same key concept that you've seen earlier, just rewrapping in this bigger concept of out of order scheduling. The benefit is this is faster. This is faster. It can tolerate the latency of longer instruction that might take a while to finish. For example, if I have to go to the memory, I have a load instruction that can take a while. It can take like 50 cycles, right? In the meantime, I can go seek out, are there anything that doesn't depend on that load? And I will run them ahead of time, right? So what are the key components that you need in order to perform the out of order execution? So you need what we call the reservation station. The first component is called reservation station. This is like a window of all the instruction that can be dispatched. So think like the instruction window that you see earlier, but a little bit more formal, right? We call this a scheduling window. So it contain, right? It contain instruction. And the instruction is basically waiting for the source input. If they're ready, you can dispatch. Then you need a structure to help reordering at the end, things like the reorder buffer, for example, so that when you finish at the end, everything finished in order. This is called the instruction window. So you have the scheduling windows that speculatively, right, execute. And you have the instruction windows that retire in order, right? So again, scheduling windows is the one that finish everything out of order. And the instruction windows is at the end. I want to make sure everything is done in order. You can implement the scheduling windows using things like reservation station. And then you have the reorder buffer, for example, that acts like an instruction window. Do you need anything else? For example, you can add a register aliasing table, right, to perform register renaming. So let's look at the reservation station first. The point, again, is to fetch everything, right? It fetch everything. So it fetch instructions to the reservation station. Even when you have a stall pipeline, just keep fetching until it's full. And it maintains all the active instructions, things like what are the operations, what are the operands. And if my operands are ready, I dispatch. So I start to run the instruction whenever I have all the source, basically. Then you can deal with register renaming again using the reservation station ID. That's similar to when I use the tag, right? When I use the tag instead of register ID, I use the tag A, B, C, D instead of the register ID R1, R2, R3, and R4. Again, we are kind of like rewrapping all the concept we learned so far, but now formalizing everything into like a defined term if you go read the textbook, right? And the register rename table, or RAT, right, consists of the tag, the value, and the valid bit. The tag, the value, and the valid bit. And typically, this is like there'll be one per execute unit. And again, I'll show you how this can be done. And again, this can be used to eliminate the case where the same register from two instructions have nothing to do with each other, but you have dependency because of write after read and write after write. That same example with like a bunch of writes to R3, right? This virtually enables the performance of having lots and lots and lots of register, even when you have only like R0 to R15, for example, only 15 of them, right? And how does the reservation station works is something like this. You have the tag, right, for the instruction, such as tag A, you want 0, 1, and you basically say, maybe I'm adding the two things together and write to R2. Tag B would be tag A, adding R0 into R3, something like that, right? So these are the reservation station. You keep fetching the new instruction in, and then when something is free, when you have all the source, you dispatch. So this one can be dispatched. Can I dispatch the second one? No, right? I cannot dispatch yet. Until A is done, right? Unless I have another tag coming in, right? Tag C that requires R1 and R7, right? And it only write the result into R4. This can be dispatched. And we can formalize the process of what we showed earlier in the table and making sure we go through the example, right? Through the algorithm we call Tomasulo's algorithm. The Tomasulo algorithm said this. So if you look at the reservation station that you've seen earlier, basically I fetch all the instruction is waiting for the source input. The reservation station is available. If they're available, right? You fetch and insert the instruction into the station. Basically, the first step is if there is free slot, fetch next instruction. So if the table is not full, I'll keep fetching. And then when I fetch, I perform register renaming. If my reservation station is not available, if it's full, I stall. If it's full, then that's when the CPU stall. So I keep fetching until this thing is full. Now, inside the reservation station, each instruction would watch for the common data bus, right? For example, if I need tag A, there'll be a bus that connects every component. And if tag A becomes available, I will announce that, hey, whoever needs A, take that value. So every single entry in the station would watch for the tag that it wants. For example, if tag C becomes available, the station that needs the tag C would replace tag C with the value, right? When both of the source are available, then you dispatch. Basically, if both inputs are ready, start executing, right? After the instruction finish from the functional units, then you broadcast saying, hey, who needs tag A? I'm done. Here's the value. That will be replaced everywhere. That's it, right? That's it. So again, putting everything together from the older example, you have actual instruction here, right? You would then fetch into the reservation station. The reservation station would have this tag destination, source 1, and source 2, right? So tag A, B, C, and D. And then you have the register aliasing table, right? That perform the renaming. And then you can have those like future file if needed, right? To make sure that you have the register file. So the benefit of out-of-order execution is this imitate data flow model. Basically, it gives you the illusion that you're running things in a data flow model. ALU would fire off the operation whenever the data is ready. And the ISA, right? The ISA is still based on von Neumann. So you can program in the typical fashion, line by line by line by line. This is called a restricted data flow machine because it's restricted. You have limited window. The reservation station is limited. It can be like 256 entry. It can be 128 entry. You cannot fetch more than that, right? And then please remember, there's nothing about memory in the picture yet, right? We'll talk about out of order execution with memory in the next lecture. We'll talk about our order execution with memory in the next lecture because content in the memory has to be updated in the program order as well. If you do load, store, it has to follow the same order. And you have to detect. The key here is to detect the dependency. So we'll talk about how to handle load instruction. How to handle load instruction. That's it for the lecture part today, because now I will give you a lot more time to work on this. So first of all, Midterm notice is coming up in 2 weeks on October 11. Make sure you know the basic material and please go through our sample exam. So if you go to our Canvas right now, you go to File, and there should be a file that just got updated called F19-ComArch midterm .pdf. And what I want you to do is, if you go in there, here's what you see, basically. So let me switch the screen a little bit. Stop sharing. And then I'll share this current screen. Here. You see the PDF that I just opened? So if I recall correctly, there was an undergraduate computer architecture exam that we had when I was a TA. I think it was 2015 or 14. But please take a look and work on question 5 right now, and we'll go through them together after the break. So we'll do a much longer break because we'll all go through this. Please download. So first, please go and download this file. Then right now, let's work on question 5 together. Well, not together. You do it first. And then after, maybe would 30 minutes be enough for this, or let's do 30 minutes. We'll be back at 11:30 to review. So the video will resume when you guys are at least have some idea about the question, and we'll go through the question together. All right. So let me first stop the video, and then we'll have another part of this video that goes over that question. All right.